Fifth-generation cellular technology, or 5G, is far more than a speed increase. It represents a paradigm shift from simple consumer mobile broadband to a modular software-defined platform. While 4G focused primarily on boosting download speeds for smartphones, 5G connects a massive ecosystem of devices, industries, and critical infrastructure with extreme reliability and low latency. The 5G ecosystem is built on three foundational pillars: enhanced mobile broadband, massive machine communication for IoT, and mission-critical services that demand near-zero latency. By utilizing software-defined networking, 5G enables precise, intelligent control in industrial environments, such as factories, where robots and sensors coordinate in real time. It is not just an internet upgrade. 5G is the foundation of the modern digital economy. While 5G is famous for its speed, its true power lies in latency. Latency is the time it takes for data to travel from your device to the network and back. By dropping delays to under 5 milliseconds, we move from simple browsing to real-time interaction. This near-instant response is the backbone of modern automation. This sub-5 milliseconds delay allows machines to coordinate with surgical precision, whether in manufacturing plants or during remote robotic operations. This is essential for high-stakes fields where even a millisecond of lag can be the difference between success and failure. Early 5G deployments used a non-standalone architecture, where 5G radio access still relied on the existing 4G LTE core network. This allowed for faster rollout but limited the full potential of 5G. The industry has shifted to standalone architecture. By utilizing a dedicated cloud-native 5G core, we remove all reliance on legacy 4G hardware. This evolution makes the core a cloud-native entity. It enables faster decision-making, significantly reduced latency, and provides a much more secure framework for modern enterprise applications. Network slicing is like creating virtual highways on a single physical road. By partitioning the network, we assign dedicated resources to specific types of traffic. Consider this example. One slice acts as a critical lane for emergency services, while another is optimized for millions of low-power IoT sensors. This ensures that high-priority data never struggles with congestion. Through software-defined architecture, network slicing allows operators to guarantee performance levels for diverse applications, effectively maximizing the utility of the network infrastructure. Sub-6 GHz is the foundation of the 5G network. It serves as the primary coverage layer, providing the reliable blanket of connectivity that allows 5G to function across vast geographic areas. Unlike higher frequencies, these waves excel at traveling long distances. Their lower frequency allows them to easily penetrate obstacles like buildings, ensuring that users have consistent coverage both indoors and outdoors. Millimeter wave, or mmWave wave, represents the highest frequency band used in 5G, typically starting at 24 GHz. These signals are the key to massive data capacity. As frequency increases, wavelengths become incredibly small, often just millimeters in length. This allows for incredibly high data transfer rates, though it comes with limitations. Because mmWave signals have limited reach and struggle to penetrate walls, they are ideally deployed in high-density areas like stadiums or city centers to deliver multi-gigabit speeds where demand is highest. Massive MIMO, or multiple input, multiple output, transforms network efficiency. Unlike traditional towers that broadcast signals in every direction, massive MIMO uses dense antenna arrays to handle hundreds of data streams simultaneously. By utilizing dozens or even hundreds of antenna elements, the system performs precise 2D beamforming. This directs energy specifically toward individual users, rather than wasting power on empty space. Behind the hardware, digital signal processing via FFT and IFFT transforms broad signals into targeted frequencies. This prevents traffic jams, significantly boosting total network capacity in dense environments. By keeping the network organized and efficient, Massive MIMO is the backbone of the high-capacity, low-latency 5G infrastructure we rely on today. Traditional network antennas broadcast signals in every direction, which is inefficient and creates unwanted signal interference. Beamforming changes this. Instead of wasting power, the antenna array uses constructive interference to focus a narrow, high-quality data beam directly toward your specific device. By tracking multiple users, the tower simultaneously manages distinct targeted beams, ensuring high-speed connectivity for everyone in the urban environment. Edge computing brings data processing closer to the user. Instead of sending data across the globe to a central server, we process it at the network edge. By moving the brain of the network to the edge, we slash latency. For robotics or autonomous systems, those few milliseconds saved are the difference between success and failure. Traditional cloud computing sends all raw data to a distant center. Edge computing, however, filters and acts on data immediately at the local node, keeping the core network free for critical traffic. This tiered architecture ensures that devices remain connected, responsive, and secure, forming the backbone of the modern 5G advanced ecosystem. We are currently entering the 5G advanced era, starting with 3GPP Release 18. This phase serves as a crucial bridge between standard 5G and the future of 6G. 5G Advanced integrates artificial intelligence directly into the radio interface. This enables smarter, real-time data management. Beyond speed, the primary focus is energy efficiency. AI models now dynamically adjust network power usage, ensuring that connectivity remains sustainable as demand scales. AI has become the central brain of modern 5G networks, moving beyond simple automation to true network intelligence. AI-driven network management systems monitor infrastructure in real time, analyzing traffic flows and system health to preemptively identify potential issues. By modeling usage patterns, the AI predicts where and when demand will spike. This allows the network to pre-allocate capacity. The AI also balances performance against power consumption. During low traffic periods, it automatically puts base stations into energy-saving sleep modes, drastically reducing operational costs and carbon footprint. 5G networks are expanding beyond Earth's surface. Traditional towers are limited by geography, but non-terrestrial networks, or NTN, bridge these gaps using satellites. Low Earth orbit, or LEO, satellites sit much closer to Earth than traditional communication satellites. Operating between 300 and 2,000 kilometers, they enable low-latency 5G connectivity. By acting as high-altitude base stations, these satellites provide critical connectivity to remote areas, maritime vessels, and aircraft, where terrestrial towers simply cannot reach. Private 5G networks act like a dedicated express lane within industrial sites, completely isolated from public traffic. This provides the reliability needed for critical operations. Unlike public networks that share bandwidth, private networks maintain an independent core. This ensures that latency remains extremely low even when many robots operate simultaneously. In modern warehouses, autonomous robots communicate over 5G to coordinate movements. Private networks ensure that no external device interference stalls production. Shipping ports also leverage this connectivity. Private 5G provides wide area coverage with high capacity, allowing remote operation of massive cranes and logistics systems. Private 5G offers superior security and performance tuning. By keeping data on site, industries achieve the control needed for modern automation. In modern smart factories, 5G enables the creation of digital twins. A digital twin is a dynamic, virtual replica of a physical production line. Sensors embedded in machines transmit real-time telemetry over ultra-reliable 5G channels. This data is fed into a cloud-based AI, allowing the system to monitor operations constantly. The AI identifies performance bottlenecks and predicts maintenance needs. By fixing these issues before they cause downtime, 5G-enabled factories achieve record-breaking efficiency levels. 5G effectively turns reactive factories into proactive AI-driven ecosystems that maximize productivity. Precision agriculture leverages 5G-enabled sensor nodes to monitor soil and crop conditions in real time. These nodes provide granular data on moisture, conductivity, and temperature. High-speed, low-latency 5G networks enable the coordination of autonomous machinery. From seeding to harvest, these units operate with pinpoint accuracy, adjusting tasks dynamically based on field data. Data flows from sensors to cloud models, which analyze field conditions. This loop triggers automated irrigation systems, ensuring water and nutrients are applied only where they are needed most. By moving from blanket application to precision management, farmers can reduce resource waste by up to 30%. 5G is the backbone of this climate-smart future, driving both efficiency and environmental sustainability. The future of surgery is being redefined by 5G technology. Because 5G provides ultra-low latency, surgeons can now operate robotic systems from miles away with near-instant response times. At the console, the surgeon's movements are perfectly translated. The 5G network ensures that the visual and haptic feedback feels exactly as if the surgeon were standing right in the operating room. This precision allows for minimally invasive procedures with incredible accuracy. The 5G data link acts as a seamless bridge, allowing specialized surgeons to assist patients regardless of physical distance. As 5G networks continue to expand, remote surgery will become a vital tool in equalizing access to high-quality healthcare across the globe. By May 2026, 5G has achieved unprecedented global reach. Over 65% of the world's population now lives under 5G network coverage. This infrastructure supports over 2.5 billion active subscriptions, marking the fastest and most expansive telecommunications rollout in history. The rapid densification of these networks continues to bridge the digital divide at a pace never seen before. 5G technology is currently serving as a massive economic catalyst, contributing over $2.2 trillion to the global GDP every single year. This transformative growth spans across diverse sectors. From smart manufacturing to logistics, 5G-enabled sales are reshaping the productivity of entire industries. Beyond simple efficiency, 5G is driving the creation of entirely new categories of jobs and businesses that simply did not exist a few years ago, effectively fueling the next era of digital industry. As networks mature, this economic footprint is projected to expand even further, embedding connectivity into the foundation of global trade. While 5G technology is significantly more efficient at transmitting data per bit than previous generations, the total energy consumption of modern networks is rising. Network density is the primary driver of this increase. Base stations now require substantially more power to handle the complex signal processing and expanded bandwidth. To address this, engineers have developed deep sleep modes. These allow antennas to power down specific components during low traffic periods, dramatically reducing idle energy waste. Balancing high-performance connectivity with sustainable power management is currently the industry's top engineering priority for the coming years. As 5G networks grow, energy efficiency has become a primary engineering challenge. To maintain sustainability, operators are shifting to green 5G strategies. One core initiative is AI-driven power cycling. Smart algorithms predict traffic patterns, putting base stations into deep sleep modes during periods of low activity. Additionally, cell sites are increasingly integrated with renewable energy sources. Solar arrays and wind turbines now power remote infrastructure, reducing reliance on the grid. Through these innovations, 5G networks are evolving from high-consumption infrastructure to smarter, environmentally conscious digital platforms. As 5G advanced matures, the industry looks toward the 2030 horizon, the era of 6G. This generation represents a fundamental shift in how networks interact with the physical world. The cornerstone of 6G is integrated sensing and communication, or ESAC. Instead of just transmitting data, the network itself acts like a high-precision radar. By analyzing signal reflections and echoes, 6G infrastructure can detect the position, speed, and shape of physical objects, effectively mapping the environment in real time. Beyond mere speed, 6G promises sub-terahertz frequencies and AI-native spatial awareness. It transforms the wireless network from a data conduit into a sensory organ for the digital world. While 4G revolutionized mobile internet for people, 5G is engineered for machines. With 10 times the connection density of 4G, it provides the robust backbone for the massive scale of the Internet of Things. 5G is an evolution of hardware, software, and AI, functioning by distributing intelligence to the network edge, enabling a world where machines communicate as easily as humans. At its core, the ecosystem bridges domains through M2M communication, linking sensors and gateways to central service platforms. Data flows from infrastructure into cloud computing, branching into critical functions like predictive maintenance and real-time traffic analysis. Diverse frequency bands manage the balance between geographic coverage and high-speed capacity, ensuring the network is optimized for every application. By moving intelligence to the network edge, 5G establishes a foundation for the future of global connectivity.